Okay. Now that we're dealing with the product rule and quotient rule, we need to understand that there are times when you have multiplication and division when it's really not worth the effort to use them. Okay? So, when the denominator is a constant or a monomial, do not use the quotient rule. You can, but a lot of people will mess it up. There are easier ways to work the problem when the denominator is a monomial or a constant. So we're going to take a look at y equals x squared plus 3x all over 6. Notice how the denominator is just 6, right? Which is a constant. Do you agree that this is the same thing as 1/6 of x squared plus 3x? Yes?
Yes.
And when you have a coefficient, it's not a variable, so it doesn't really count as multiplication. So you can just hold the coefficient and take the derivative of what's in the parentheses. Now you couldn't do that if that was a 1/6 x. You can only do that because it's a constant. So it's really easy to just take this derivative this way. That's the only time you can take a derivative with something outside the parentheses like that. Now if you tried to do the quotient rule on this, we would have y prime equals low d high minus high d low. What is the derivative of 6? 0. And a lot of people miss that, and so they forget that 0 there, and it messes the whole thing up. All over low, which would be 6 squared, or 36. So if we did the quotient rule, it kind of looks really ugly, and you can see already it's taking a lot more effort than this. This piece all goes to 0, and we're left with 6 times 2x plus 3 all over 36, which will reduce to 6 over 36, which is 1/6 of 2x plus 3. So you could write the 1/6 out in front, or you could just write it as 2x plus 3 over 6. So you will get the same answer, but it's going to take you more effort. So if you train yourself when there are constants on the bottom to do it without the quotient rule, it'll save you a little bit of time and headache. In this example, we have a monomial over a constant. If we want to do that without the quotient rule, we would simply envision it as 5/8 of x to the 4. And then we could just do the power rule. F prime of x is equal to, what is 4 times 5/8?
4x.
That would be,
Over 8.
it would be 28 or 5/2, right? 5/2 of x to the 3rd. So it's really easy to do that without the quotient rule. It would still work with the quotient rule. So if you did get in a hurry and you were going to do it with the quotient rule, you would have low d high minus high d low over low, and then you would clean it all up. This would go to 0. We would have 160x cubed over 64, which I'm hoping reduces to 5/2. Does it? 160 over 64?
Yes.
Yes. Yeah, okay. So 5/2 x cubed. Either way, you would get the same thing. But I think it is easier when there's a constant on the bottom not to use the quotient rule. For this example, we have g of x equals -3 multiplied by 3x minus 2x squared, all divided by 7x. And the very first thing I'm going to recommend is get rid of those parentheses. And before you do anything, just deal with that -3. We don't want to have multiplication and division going on. So we're going to go ahead and distribute the top. And we have -9x plus 6x squared. All over what? And in this case, do you guys see that we could factor out an x and cancel it? And if we factored and canceled that x, what would be left? -9 plus 6x all over 7. Okay? Now there are a couple of ways you can proceed from there. It just depends on how your brain sees it best. When I look at that, I see it as -9/7 plus 6/7 x. Like, I see it more like when we do slope-intercept form and we divide, you know what I mean? I see it just split up already. Some people don't. It just kind of depends on how you see it. And if you split it up and then take the derivative, what's the derivative of negative 9/7? 0. And what's the derivative of 6/7 x?
6/7.
So it started off looking, whoa, there's no x there, right? Just 6/7. It started off looking like it was going to be really complicated, but it turned out that once we did a little algebra to it, it was really simple. So you are always allowed to simplify as much as you want before you start the calculus, like before you start taking the derivative. So be on the lookout for that because it can simplify your life tremendously. If we take a look at y equals 2x squared minus 4x all over the square root of x, and we try to do that without the quotient rule, what we have to do is we have to split it up and divide the square root of x into both of those. So if you envision it this way, you could go ahead and simplify that down and get it as a string of terms rather than something multiplied or divided. How would I simplify 2x squared over x to the 1/2?
2x.
What's 2 minus 1/2? We subtract our exponents and we get, that would be 1.5, right? So that would be 3/2. And then 1 minus 1/2 would be 1/2. Like that? Okay. And that cleans it up and allows you to do the power rule to it. So we have y prime equals 3/2 times 2, which is 3x to the 1/2 power, minus 1/2 times 4, which is 2x to the negative 1/2 power. And then I don't deal very well with fractional exponents. I like radical forms, so I'm going to go back and put this as 3 square roots of x minus 2 over the square root of x. And then up until now, I've allowed you to leave your answers in that form, but starting today, I want least common denominator every time. So we're going to start working on that. To get a least common denominator of these two terms, we would use, what would be my least common denominator?
The square root of x.
The square root of x. Okay, and I would multiply this guy by what's missing. So what's missing on top and bottom here?
Square root.
So I'm going to put a square root of x here, and a square root of x here, and that will convert them to a shared common denominator. And then you just have to multiply 3 square root of x times square root of x, which is just 3x. What's missing from this guy? Nothing, so we just leave him. So getting a common denominator is not that bad. Usually when you do that, when you get a common denominator, you won't have a radical left on bottom, which I'm sorry, you won't have a radical left on top. It will remove the ones from the top and put them all on the bottom, which I prefer. So for our last example problem of when not to use the product and quotient rule, if you are distributing a monomial, it will always be less trouble to just distribute it rather than to use the product rule. So if I have x to the 1/2 times x squared minus 6, the easiest thing to do is to envision this as x to the 1/2, not in radical form, and then we will distribute by adding our exponents, which is x to the what?
5/2.
5/2.
Got that part right.
Okay. Minus 6x to the 1/2. Then you just take the derivative using the power rule, and we have 5/2 x to the 3/2 minus 1/2 times 6 is 3x to the negative 1/2. And then we can convert that into radicals. So we have 5 over 2 square root of x cubed minus 3 over square root of x. And we do need to get a common denominator, but we're running a little low on time. So I'll pause that here and I'll finish that later. And then next time, just remind me if you're having trouble with common denominators to let me know. So if we want to find the common denominator here, we will look and see that it is going to be 2 square root of x. So we look and see what's missing from this fraction, and it looks like we're just missing the square root of x, so we'll multiply that on top and bottom to give the common denominator. And if we do that, what we'll have is 5 times the square root of x times the square root of x cubed, which would really be 5 square root of x to the 4th. And then this one is only missing the 2, so we'll multiply this one by 2 over 2. And that will give us minus 6 over 2 square roots of x. To clean that up as far as we can, the square root of x to the 4th is just x squared, so we have 5x squared minus 6 all over 2 square roots of x as our final derivative. Notice again that when you get common denominators, most of the radicals disappear from the top and just show up in the bottom. So it actually ends up making it a little bit prettier than if we had stopped, say, here. And from now on, we are going to take our derivatives all the way to a least common denominator, because when we get further over into the applications, you will need to have a common denominator to sort of solve them equal to 0.